Hey team, welcome to the numbers game. I'm Coach T, and in this tutorial we'll be using the Divergence Theorem to calculate flux. Let's get started. In our example, we're given a field with a solid that's bounded by two paraboloids, and we're asked to use the Divergence Theorem to calculate the flux. So this space is bounded by two paraboloids, and since we know what those two paraboloids are, I'm going to go ahead and graph them. Our first paraboloid is 12 minus x squared minus y squared. And our second paraboloid is 2x squared plus 2y squared. It's a rough sketch, but that's basically our bounded surface. So now let's start solving for the flux. We'll start by writing our field as a vector. As a quick refresher, the divergence of our field equals the partial derivative of p with respect to x plus the partial derivative of q with respect to y plus the partial derivative of r with respect to z. We see that the partial derivative of p with respect to x equals 1/2. The partial derivative of q with respect to y equals 0 because there is no y variable in q. Same goes for r. The partial derivative of r with respect to z equals 0 because there is no z variable in r. So we see that the divergence of our field equals 1/2. Now that we've found the divergence of our field, we can start solving for the flux. We're able to find the flux by evaluating the triple integral of our divergence. So for us, we have the triple integral. Now if we take a look at the two paraboloids that we graphed, and I'm actually going to switch these around to better illustrate this. 2x squared plus 2y squared is our lower bound, and 12 minus x squared minus y squared is our upper bound. So our integral is bounded by 2x squared plus 2y squared as the lower bound, and 12 minus x squared minus y squared for the upper bound. Now again, this is the triple integral of our divergence, which is 1/2. Alright, so let's solve this integral. We'll start by moving our constant to the outside of the integrals. And we see that the integral from 2x squared plus 2y squared to 12 minus x squared minus y squared with respect to z equals 12 minus x squared minus y squared minus 2x squared plus 2y squared. So we'll just subtract our lower bound from our upper bound. This leaves us with 1/2 times the double integral of 12 minus x squared minus y squared minus 2x squared minus 2y squared. Now at this point we're going to switch to polar coordinates. Note that x squared plus y squared equals r squared. And with that in mind, we have 1/2 times the double integral of 12 minus r squared minus 2r squared times r. I'll just simplify this a little bit. And now we'll evaluate our inside integral. We've got the integral from 0 to 2 of 12r minus 3r cubed with respect to r. And this equals 6r squared minus 3r raised to 4 over 4 from 0 to 2. And this simplifies to 12. This leaves us with a half times the integral from 0 to 2 pi of 12 with respect to theta. This, of course, simplifies to half times 12 theta from 0 to 2 pi, which gives us a final answer of 12 pi. And there you have it. That's how you calculate flux using the divergence theorem. If this video was helpful for you, give it a thumbs up, like the video, and subscribe to the channel for more math tutorials. I'm Coach T, and thanks for watching The Numbers Game.